the air quality, on behalf of the air quality monitoring team. And this picture here, just to show, is a view from one of our monitoring sites. This is the US Virgin Islands, looking north. So I'm representing the air quality monitoring team. It's a diverse group and it's a lot of people. They've done a ton of work. I'm just consistently awed by all the things that we're able to do. And so what I'm here is just being a mouthpiece to sort of show some of the many things that are done by the AQMT. For obvious reasons, I don't have a more recent picture. We've grown a little bit since this, but I know a lot of you are on this call right now, so I hope I do you justice. So we're the monitoring team. So the primary thing we do is monitoring, and I mentioned IMPROVE and CSN. Those are the two big networks we operate. So let's get into talk about those. So the first is IMPROVE. This is a somewhat tortured acronym, stands for the Interagency Monitoring of Protected Visual Environments. It's a long-standing network and began back in the late 80s with only 30 sites. It was expanded in 2000 about to around 160 or so sites. And it's designed to measure visibility. It's looking at pristine areas. It's where we want to protect the ability to see from one side of the Grand Canyon to the other. There's these so-called Class 1 areas. They're in national parks, national forests, national wildlife refuges. And so they're sponsored by the land management agencies that run those lands, Park Service, Forest Service, et cetera. Also get buy-in from state governments who participate in the network and a couple of international governments as well. And our team, the air quality monitoring team, has operated this network from its inception back in the 80s. We also designed the samplers. And so here's the samplers, basic setup. These are filter-based measurements. We collect samples that are 24-hour integrated. So open up the filter, collect air for 24 hours. We do it every third day. So it's 1 in 3 day sampling. And then there are 4 filters on each sampler. So, and we call these 4 different modules, and they have, they're designed to collect different components. So they have different types of filters, Teflon, nylon, quartz, and then they have different size cuts. We have 3 PM2.5 size cuts and 1 larger PM10 size cut with a Teflon filter. And these were designed for clean environments. They're in pristine areas. So that means they have a high flow rate and a small filter to really concentrate the filter, the particles on there so we can measure small quantities. And we also maintain these samplers. They're out in remote areas all across the country. And we have a field group that visits all of these samplers every 2 years to do maintenance. And there's lots to do there. But in addition to that, there is the Chemical Speciation Network, CSN. CSN is a lot like IMPROVE, but it was designed for a slightly different purpose. It was established by the EPA, the Environmental Protection Agency, around 2000 for speciated monitoring of PM2.5 in urban areas. And so, and the goal is not to protect visibility or to understand visibility, but to look at public health impacts. That's why they're in urban areas, and assess long-term trends, quantify sources, study emission reduction strategies, that sort of thing. So these are also 24-hour integrated filter-based samples that are some of them are 1 in 3 days and some of them are 1 in 6 day, but they're on the same sample schedule as IMPROVE. So if it's a 1 in 3 day, if it's sampling day for IMPROVE, it'll be a sampling day for CSN for the 1 in 3 sites. They measure the same things. I'll get into that in a second. And our involvement, UCA Davis involvement, the AQMT involvement with this has not been nearly so long. We won the contract to take on the laboratory analysis of CSN samples at the end of 2015. So we're now about 6 years worth of history of running that network. Together, they are quite complementary, and they're sister networks. The measurements are very similar, not identical, but very similar. And they cover a broad swath of the country. You notice here, the red is the CSN sites, blue is IMPROVE sites, because IMPROVE is mostly in national parks and rural areas. It's more focused in the West, whereas CSN is more in the urban areas while people are, so it's more concentrated in the east. We have sites in Alaska and Hawaii. This is Puerto Rico, the US Virgin Islands, which is the site from the picture at the beginning. We also have this very interesting research site here, and this is on an island which is directly next to North Korea, but it's actually owned by South Korea. And it's a research station. It's very interesting. It's sort of halfway in between Seoul and Beijing, so it gets lots of urban pollution. And so it's an interesting site to look at. The yellow points here are important, and those are where we have both CSN and IMPROVE essentially co-located in the same spot. And that gives us an ability to validate and compare the two networks, and we've discovered some interesting things looking at the two data sets together. So what do they measure? First, just we got about, between the two of them is about 300 sites. We sample every third day. IMPROVE is rural, CSN is urban primarily. They have different objectives, but they're measuring more or less the same things. IMPROVE measures PM2.5 total mass. CSN used to, but they cut that to save money with the thinking that they are generally co-located with federal reference method PM2.5 samplers. IMPROVE has a PM10 inlet for PM10 mass. CSN does not, but otherwise they're very similar. They both do ions, anions by ion chromatography. CSN also does cations. They both do elements by X-ray fluorescence and carbon by thermal optical analysis. So that's at the high level. I'll show you some data in a little bit, but just a taste of, there are some challenges to running these large scale regional networks that are, some of the sites are quite remote. For example, there's snow you have to deal with. This is very recent from Bliss site in the Sierras. After snow, here's some inlets here that are just about to get overtaken by the snow. So the operator has to try and clear those off. But there's also windstorms. This is in Southern California. We have lost some samples there. And then, this was in Wyoming. This happened earlier this year, I believe. There's a sampler that was just overtaken by wildfire. So the field groups kept busy, not just with routine maintenance, but complete repair and rebuild of these sites. But even if your site stays up, there's still issues with Mother Nature. Here's an example of some field notes from a maintenance visit showing that, yep, there are spider webs inside the cyclone. This causes problems. This changes our flow rates, changes collection, and so we have to invalidate data. There's even larger animals that get in. This is a note from a CSN validation showing that there was blockage, which is a frog that prevented flow from the channel. So lots of things we have to be wary of as we deal with these 300 sites. But what do we get from working through all this? We've got a lot of really interesting data. And so I'm going to talk a little bit about some of the features and what's special about these networks. The first is that this is this long historical record. This is a site, the Great Smoky Mountains National Park, that's been running continuously in the same spot since 1988. And not only that has it been running in the same place, but the methods have remained the same as much as possible. We try and maintain this consistent long-term record. And so you're able to really see these long-term trends as we go into our fourth decade of measurements here. What I'm showing at the top is sulfate. And, it has from 1990 to about 2010, this very characteristic, what we learned about, sulfur from coal-fired power plants in the southeastern United States and Ohio River Valley. Every summertime, we have these sulfate episodes. And then something changed as the emissions drastically reduced from changes in policy and the introduction of more natural gas, that sort of thing. The summertime sulfate has essentially disappeared. It's evaporated, and it's been gone now for a whole decade. And so it's really changed the characteristics of what makes up the aerosol in the southeastern US, and you know, a big success story for air quality in the US. On the bottom here is OC, that's organic carbon. And you know, it shows a slightly different story. I've zoomed in a little bit. You can see that if you look closely, it has this trend does go downward slightly. But not nearly so much. This used to be representing, you know, you're looking at 10, 20 micrograms, 10, 15 at least at the high points, whereas these were only, you know, 3. And now when sulfate is down below 5, that means we've completely changed the characteristics of what makes the particles in the Great Smoky Mountains. In addition to this long time history, we also have a lot of breadth in terms of spatial coverage because we have all these sites. We've been running them for a long time. Here's the idea of how to look at this across both time and space. What I've done here is taken, most of these are a single site, but for some sites, for some areas, we have more than one site within a degree of latitude and longitude. So those are averaged together. And I'm looking at mean annual summertime sulfate from both CSN and IMPROVE smushed together. So each of these is a little time series, and each point is a year, June through August, sulfate concentration on average. And then in the lower left-hand corner here is the legend for this plot, but it's also all of these plotted on top of each other. And I say it's the legend because this gray line here corresponds to this, so that can give you a sense of the, you can map them onto each other. The colors here, I've colored by lines of longitude. So the lighter blue colors are more to the east. And so that helps you see, you can see a couple of big things from this. One is, of course, in the right around 2000, the big expansion, the addition of CSN to the network, and a big expansion of IMPROVE so that we get a bunch more sites, especially in the east when CSN kicked in. Also, you see that this sulfate was predominantly in the east and that it's disappeared. So similar to what we saw before. But this is only possible by having these large, long-term, large-scale networks. Of course, this is a speciation network, so we're not just talking about single species or total PM. So the important thing that we can do that can't be done by other networks is to characterize PM mass. What is in it? What's it made out of? Here's some sites with reconstructed mass showing a few different interesting patterns or just differences between them. What I'm showing is the monthly median reconstructed mass, which is mass made up of these different large components sort of added on top of each other. We look at Point Reyes here in California, right on the coast. It's mostly this blue, which is sea salt. Makes sense. If you look at Fresno, which is, this is one of the few urban sites that we have in IMPROVE. It's a much dirtier site. It's one of the dirtiest sites, but it has a strong wintertime component that's driven by the red, which is nitrate, in addition to residential wood burning, and then this black elemental carbon, which is some burning and some diesel and other anthropogenic sources probably. Sawtooth Wilderness in Idaho here is generally very clean, except for in the summertime when they get wildfires, which they get fairly regularly in this part of the country. And then they get this increase, especially in the organics. Everglades is interesting because it has this high sulfate. Still, sulfate makes up a large component during this time period. And then this brown here is from soil. We don't measure soil directly, but we estimate soil by measuring elements that are in soil. And so they get this soil from, say, May, June, July, August, and this is from transported dust from Sahara dust storms that they're easy to see in the Everglades, but we see them throughout the Southeast. Speaking of those parameters that help us get soil, because we can look deeper at those. Here's a cluster analysis combining the two different networks together, and you can see that Soil is not created equal across the country. We have different signatures, different patterns. You know, the soil that comes, that's driven largely by the Sahara influence, is very rich in silicon and titanium, and has this temporal pattern that it comes in the, you know, comes at this time of year. This area right here has much higher calcium than the other areas. And so there's just a lot of information that can be teased out of the different pieces. We also see both rare and unusual events. Here's one that's actually not that rare, but it's springtime. We have very high potassium in Kansas. And this map here has an automated scale so that the lightest color is between 0 and 100 nanograms per meter cubed, so down up to 0.1 micrograms. And then up here is 500 and 600. That's the highest, which is this site here in Kansas at the Tallgrass site. This is the day. So there, it's much, much higher than anything else in the network. So what's going on there? Basically every year, the ranchers burn the Flint Hills as part of land management practices in order to improve the cattle feed and make the cattle fatter. And it just so happened that this day, those smoke plumes happen to hit on this site. Now, that's not that rare. This happens every year, but the advantage of having this, another advantage of having this long time series is that we can see events that are quite rare. This is something that Warren White, who's on the phone, has looked at. We have this is a time series of sodium, particle sodium, and this is Badlands, South Dakota, so nowhere near the ocean. And the concentration here is 5 micrograms of sodium. That's very, very high. And you see this the regional nature of this event by these high values that are all around this area. And he did quite a bit of work on this, trajectories and all sorts of things, and was able to trace this to a rare incursion of Arctic sea salt, just like this frozen air coming down. And it's crazy because this is also a site that has been operating since 1989 or so. And in those 40 years, this has occurred exactly once. And this is the sort of thing that you can only really see with sort of this long time series. Of course, we can also, we measure things that are less benign than sodium. Here is looking at vanadium. This is from the IMPROVE network. And this is from a paper that Nick Spada and Nicole Heislip worked on and submitted, let's see, a while ago. And the blue circles are from 2011 and the red circles are 2015. And the larger the circle is, the higher the concentration of vanadium. And you can see that, the red circles are generally smaller than the blue circles, but particularly on the coasts here, that's where they were high and now they're low. And what this green outline here represents is an emission control region. Basically, there was a rule put in place that said that the ships had to run under cleaner fuel once they entered this region. And we believe that this is the impact that you see from this reduction, this change to a lower sulfur coal, which we can see also in a reduction in vanadium. I looked at this, by the way, this runs from 2011 to 2015. We have more recent data now, so I looked at it also in more recent time, and we see the same thing with the CSN network. These plots are showing network-wide concentrations, network-wide values. So that what's important here is the top of the bar. The top of the bar is the network-wide 90th percentile, and each color represents a year, and each of these clusters is a month. So you can look at any month. Let's look at July. From 2015 to 2020, a precipitous drop in the highest concentrations of vanadium across the network. All right, I'm gonna take a drink because we're gonna change focus a little bit. So this is a lot of data. How do we get all this data? How does it work? What happens here? First of all, this is an analytical factory. It's a little different from an average research lab. We have a lot of filters to process. 125 sampling days, so every third day. So if we have one site, that's that many samples. We have 165 sites for the IMPROVE network, and we have 4 filters for each sampler. So that's 80,000 filters a year for the IMPROVE network. For CSN, it's a bit fewer since we only have 3 filters and some of them every 6 days. So that's still on the order of 125,000 samples a year, which is 340 or so a day, or 14 for every hour. But that includes, Sunday night on Christmas when we're not working, but maybe our instruments are. So we're processing continuously and keeping it going. And it's a sort of assembly line operation. And so here is, I'm using IMPROVE as the example here. CSN has a similar but slightly different flowchart. But basically, walk through here. We have the 4 different filter types. 2 Teflon filters, a nylon and a quartz filter. The Teflon filters get gravimetric analysis, so they have to be taired, they have pre-weighed, and then all of them are loaded into cartridge prep and put together and put in boxes. This is all done by our sample handling team in the sample handling lab, and those are delivered to the field. And then in the field, we are partnered with our federal partners, who are people like park rangers and wardens and that sort of thing, people who work for the Park Service, the Forest Service, and they take the boxes, load them into our samplers, and then take the sampled ones, put them in the box, and deliver them back to the truck, and they come back to us. We take the sampled filters, and it depends on what analysis, what filter type they are, which way they go. So the Teflon filters, they get post-weighed, and then they go through a series of analyses at our lab. And then all of these analyses are non-destructive, so eventually they end up in archive. Then the nylon filters go to another contractor, RTI, for ion chromatography, which is a destructive analysis. So those filters are gone. For IMPROVE, we deliver the quartz filters to DRI for thermal optical analysis. For CSN, we actually do that analysis in-house. So just a bit about the laboratory analysis. I don't have time to go into all the different things that are done there, just to get a sense of what we have, what we offer. We have 2 automated weighing chambers that do gravimetric mass. They can load, they have a robotic weighing system that can theoretically load 400 samples per set. We have 5 epsilon 5 X-ray fluorescence analyzers for elements. We have 6 Sunset OC EC thermal optical analyzers for doing organic carbon, elemental carbon, and the fractions thereof. We have 3 FTIRs, Fourier transform infrared spectrometers, which we can get OC EC similar to the thermal optical, but also carbon functional groups, sulfate, soil, mass, a few other things that we're getting a little bit more on that later. We have our own custom instrument, the HIPS, which does a light absorption measurement. And finally, I thought I'd add here at the same time, we also have an aerosol sample generation chamber, which we use to develop reference materials and standards, because this is really something that is needed in the community. It's hard for us to find standards that really mimic atmospheric aerosols at the right kind of concentrations we're looking at for calibration and quality control. I mentioned we have filters that go to archive. I just want to say we have a lot of filters. We have over 1 million field sampled Teflon filters from IMPROVE in our archive. We also have hundreds of thousands from CSN, 50,000 also we took on from the no longer existent search network, the Southeastern Aerosol Research Network that was in the Southeastern United States. So these filters have been sampled in every condition you could imagine. So did put together a little prototype application for trying to you know, find these filters for future access. Like, for example, let's say, you know, just looking at the most recent Teflon filters from CSN, they say, okay, we have 63,000 filters, but I'm only interested in this region during January, February, and December. Okay, there's 2,000 some of those. But what I'm really interested in is samples that really have high nitrate. And so I could say, okay, well, nitrate greater than 10 micrograms per meter cube. We have 119 of those. Here they are. And potentially those are available could be made available for analysis. So I am interested to hear from people if they think that this would be a useful resource to them instead of having to go conduct a field study of their own. Once the data, once we've done all that stuff with the filters, we obviously have a lot of data. You know, we have about 2 million records for each network for each year. And we have a team that does data validation to ensure that what we're putting out is the highest quality possible. And this is all done by custom tools. We have our own software engineers. We have a team that helps build these interactive things and are connected to our databases. There's a similar flow chart for this as there is for the physical data. This is for the electronic data. It comes from all the instruments as well as the controller. It goes into our own custom designed database. We have our own processing code, which turns that into the concentrations, uncertainties, and detection limits. Then they go through a rigorous data validation where we request reanalysis, flag suspected things, add a lot of comments, and then finally deliver them to the public through the US EPA's AQS system and the Fed database. Here's just an example of one of the tools for validation that we use. This is a cross-filter comparison. Basically, we take advantage of the fact that we measure some of the same things on 2 different filters. So for example, this flirt plot here, the time series is showing, in the red is showing the sulfur as analyzed by XRF from the Teflon filter, and the blue is sulfate as analyzed by ion chromatography on the nylon filter. This gray box and the circles within it are plotting the ratio that we expect. And so as long as these circles are within these boxes, that means that they're tracking together, because predominantly the sulfur in the atmosphere, in the particles, is as sulfate. If these deviate for a lot, we can interrogate those, click on it, figure out more, learn about comments, talk to the lab, request reanalysis, figure out if something happened with the sampling, and try and understand which of these or both of these is wrong or not. Okay, so that was sort of the operational bit, but I wanted to talk a little bit about what we do in terms of research. And the research that we do is primarily driven towards making the network operation better and pushing that forward. So I have a couple of just tidbits from around the groups and looking at a few different things. I have two samples on how we're improving sampling technology, a couple on method development, and then just a little bit on broader study involvement and international work. So first of all, sampling technology. We have various issues. So this is an example from CSN. The problem is we've cleaned up the environment too much, and CSN wasn't designed for that. CSN, unlike IMPROVE, has a quite low flow rate and a large sample deposit area so that the total mass loadings we get are low. And as the air is cleaned, it's made our detection limits too high for us to be able to see what we're collecting. Now, the standard CSN filter is a 47 millimeter diameter, which means it has this sample deposit area, about 12 centimeters squared. Now, EPA proposed and designed for us a metal insert that can hold a smaller filter, a 25 millimeter filter, which has a smaller sample deposit area. So that would concentrate the sample into a tinier area. So we have a factor of 3 increase in mass loading. So theoretically, we'll be able to detect more. It's a complex system, and it's a complex piece of machinery to get this all together and fit just right. And it turns out that when we were doing our tests on it, we were not getting the same results. The concentrations were biased low with the 25 millimeter inserts. And that's because we discovered that it leaks. Now, Chris Wallace, one of our mechanical engineers, discovered this and also did the leak test. But beyond doing that, the real thing is, the exciting thing is that he designed a new, better system for that. So now we have this prototype, much simpler adapter that was originally made with a 3D printer and prototyped and now going out for machining. And it's a snap together thing, and it's based on our experience and knowledge in operating the IMPROVE sampler. Now, this is to go on the CSN samplers, which are not ones that we developed. So hopefully that will help with that detection limits on the low concentrations. We also have a problem, though, on the opposite side. IMPROVE, as I said, was a high flow designed for clean environments, but sometimes we don't get clean environments. So here is a picture from September 12th, 2020. Really bad day across the world, but here in the West as well, super smoky. And so what I'm showing here is all of the IMPROVE sites. Anything with words on it was invalidated because of some issue, something went wrong. But a large portion of these they were clogged or destroyed. And both of these are caused by too much sample, too much smoke. And the next day here's next sample day, a bunch of clogged filters, as well as some destroyed filters. And the destroyed filters are invalidated because they get so much of this sticky smoke that they stick to the screen. And so when we try and pull them off, they're quite thin. They just get destroyed. They get peeled off. So basically what's happening here is we're either clogging it because we have too much smoke, or it's got so much smoke that it's getting stuck. Here is a plot of flow rates from this time period at Yost, which all the IMPROVE sites have these four-letter codes. This is Yosemite National Park. And so remember, so this is showing 3 of the modules, the Teflon, nylon, and quartz, so each filter. And this is 15-minute flow data. And each of these little wiggles here represents a 24-hour time period. Remember, it's 1 in 3 sampling, so we have 1 day on and then 2 days off and another day on. This is what it looks like in clean, normal conditions. They sort of sit around nominal, and they go up and down as a function of temperature. That's normal. In moderate smoke, they start to clog. The flow in liters per minute drops. But then if the smoke is really heavy, then they crash. And below a certain liters per minute, but below a certain flow rate, our measurement becomes unreliable. And finally, there's no way we can calculate a flow, which means there's no way we can report a real concentration. So all of these are lost samples, which is a real shame, because this is the time period when we most want to know what the concentrations are and what the conditions are. So we're implementing a protocol to be able to shut off the sampling after the flow reaches a certain point. And this is only made possible because we recently redesigned and implemented new controllers with smart electronics and smart software, thanks to both our field team and our software team. So that's going to be going in hopefully this year, we'll see. Okay. So changing gears now to talk about method development a little bit. I talked about the HIPS instrument. I'm not going to talk about it much, but the point of this slide here is just to show that the importance in running a long-term network. The important thing, one of the most important things, is understanding if the trends you're seeing in the data are real. And it's more challenging than you would think, because it's almost impossible to keep everything exactly the same. After 30 or 40 years, not only do parts die and need to be maintained, but sometimes the parts you designed originally don't even exist anymore. And so you have to get new things. Filter manufacturers change their source of Teflon, things like that. So being able to tell whether the changes you're seeing in the network are real and atmospheric, or just a source of, or just something that was caused by something that happened in the field or some change that happened in the laboratory is really important. Here's some work that Warren did showing we delivered data using the HIPS instrument. It reports absorption. The FAB stands for filter absorption. And between 2003 and 2017. And then we got a brand new instrument. We rebuilt the instrument from new parts. It was getting old. We needed to replace some things. We got better detectors, all these sorts of things. And then calibrated it independently, but then said, well, is it measuring the same thing? And so this is a reanalysis and a comparison against the reported data versus the reanalyzed data, showing just the beautiful reproducibility of this. So this is really cool to me. Another cool thing is the way that these data are used, outside of what we do, outside of the original intention, and how they can help the larger, broader community. So this project, and this picture comes from the website from NASA Maya. Maya is a new NASA mission. The satellite hasn't launched yet. It stands for the Multi-Angle Imager for Aerosols. And this mission's goal is to map particle species concentrations and relate them to public health. So epidemiologists are involved in the project. And they're only, because they have this satellite which aims at the same place multiple times. So it has so it's able to get the same place from different angles. And that's a way that it's hoping to help understand that it can get speciation doing that. So it only looks at specific study areas. But it's relating those our measurements, it relates ground-based speciation measurements to the satellite observations using some fancy modeling. And the exciting thing here is that our data, the CSN and improved networks, are the data that they will be using to anchor all of this information. Of course, those aren't available all over the world, and Maya has some international places, so they have to look elsewhere for some of that. More on that in a second. Okay, just a couple more slides. I mentioned FTIR, and this is the work of Ann Dillner's group, but she's been developing these methods for FTIR for years now, and we've got a lot of stuff out of them. But what she's showing here is 3 spectra from the FTIR instrument for a site, the Fresno, California site in IMPROVE, and basically just examples that show all of the various things that you might be able to see with FTIR, including these different functional groups and things like nitrate, sulfate, and by understanding these different wiggles that are caused by the different types of bonds. So this is being used right now. We are running FTIR in IMPROVE. We're running FTIR in CSN, but it's still kind of in a research mode. But we've been working towards transitioning this to becoming more part of our operational system. So hopefully moving forward, we'll be able to do that. One of the ways that FTIR has been used is looking at some of these international networks. So looking beyond our networks, for example, there's the Spartan network, which is not run by us. And what's cool about Spartan is it's explicitly in these really polluted places relative to the sort of measurements that we have. So getting involved in these networks is exciting as well, because it allows us to actually see some data from some really different kind of aerosols. And so FTIR is included in this project to look at OC and EC. And I just have here a couple of examples, early examples that Anne provided of some of the cool spectra you can get from these other places, showing, really able to see some different apportionment. Abu Dhabi with like very high crustal, that makes sense, very high ammonium. Nigeria, we see burning. Hanoi, see aromatics that we believe be from rice burning. And Halifax is very, very clean, but they still have coastal and ammonium and a few other things. So how do you get the data? The AQS system is sort of the official way to get the data. That's where we deliver the data. We also deliver the data to the Fed database. It's worth looking at. It in some ways is a little easier to use than AQS and essentially has the same things when it comes to both CSN and IMPROVE data. Be patient. It can take up to a year. We're trying to speed that up, but generally there's a lot of steps involved, as you see, and so it can take some time if you're looking for 2021 data. It's not all there yet. But I think the most important thing is just to reach out to us. I feel like people should be contacting us more to learn about our data, to use our data. I'm hoping it's useful to you. So with that, thank you very much for your time and for listening. Acknowledge our funding and all the management from the Park Service and EPA. Tony, who directs ACORC, Nicole and Ann, who are my co-associate directors, and especially Nicole, who's really run this operation for many, many years, and then also the people here, Nick, Chris, Ilya, Warren, and Jason, I believe, are all the people whose stuff I stole to include in this presentation. So if you have any questions, please don't, you can ask me now, but also reach me later. I just, this plot, or this this letter right here just shows, this came at the beginning of the pandemic, March 31st, 2020, when the campus was shut down completely. Our sponsors were very concerned that we would be losing this critical resource to understanding air quality. And so they sent this letter basically saying that essentially we're essential. This is essential function. And so I really feel that way. And thanks, I appreciate your time.
Great, thank you for the excellent talk. So we have some time for questions. So I see Heather, you have a question. Please go ahead.
Yeah, hey Sean, I was hoping that you could talk more about what kind of public health outcomes that the NASA study is aiming to link to the chemical species.
Yeah, that's a great question. So the NASA study has some primary target areas that it's identified. And one of the reasons it specified those target areas is because it has identified a cohort and is working with a PI on the epi side for a specific outcome. So there's several of them, so they're not all the same, but and I don't really know what they all are. So I would recommend going to the Maya website, and they have the sort of what the primary target areas are and who the people are that are running those and what studies they've identified specifically for what outcomes they're looking at.
Great, thank you.
Mm-hmm.
Great. Any other questions?
Yeah, I have a question. So at what wavelengths does the HIPS instrument measure the light absorption? So I'm wondering if it just only measures light absorption at a single wavelength.
So it's a good question. The reason I laugh is because at present, the data we report is a single wavelength. But we are actively testing a multi-wavelength HIPS instrument, which I believe has 5 channels. Let's see,
it's 4 channels.
Oh, 4. Okay, Nick's online. Nick, you want to tell her what the channels are for the new one?
Yeah, we have 450, 553, 630, and I think 750. Or 730, and those were chosen to try and match other sorts of field equipment that we may be co-located with, as well as availability and the different lasers that would work together. But we are hoping to get a good spread so we can look at things like wavelength dependence and add that value to the filter absorption measurements.
Yeah, exactly. I hope different absorption at different wavelengths can give us more powerful results. Yeah.
Yeah.
Okay, so maybe time for one more question, short questions. Any people? Okay, if not, then let's thank Sean again. I think Sean will be happy to answer any questions you may have. You can be reached out later. And then I will take the last minute to introduce our next speaker for the next seminar, which will be on February the 3rd. So Dr. Colin Rosales, who joined AQRC last year, will be presenting on February the 3rd. So her bio and abstract will be sent out next week. And also please keep an eye on our email because we might change to in-person or the hybrid mode if allowed by the university. So thank you again and have a good day.
Great, thanks Sean, great job.
Thanks, Ian.
Fascinating stuff, see ya.